Hi everyone, I am Verónica Miró. I am a postdoc at UNAM in Mexico City, and I will present my work entitled The Symmetric Coefficient and Fischer Models with Bottlenecks. Most of this work is available on the archive, and it is joint work with my two postdoc supervisors, Adrián González Casanova and Arnaud Cyril-Gécouze. I will also present some ongoing work in collaboration with Emmanuel Scherzer and Elise Cardoncuff from Collège de France and Jean-Bernard Hayet from CIMAT, Mexico. To begin with, I will recall the Fischer model, which is the most classical model in population genetics. It has a fixed population size, n, discrete generations, and each individual chooses her parent uniformly at random. If we consider the fraction of type 1 individuals, here type 1 is the pink, and we rescale time by n, and we let n tend to infinity, this process converges to the Fischer diffusion, which is the solution of this SE. Alternatively, if we sample individuals from the last generation and we follow their ancestors backwards in time, this blue genealogical process converges when n tends to infinity to the Kingman coefficient, which is the process valued in the partitions of the natural numbers where each pair of blocks merges at rate 1. N of t, the block counting process, jumps from n to n-1 at this rate. These two processes, x and n, are extremely related. In particular, we have this moment duality relation, which relates the moments of the diffusion to the probability generating function of the block counting process. The kind of questions that we want to ask here is what happens to the genealogies when the population does not follow a Fischer model because it has a varying population size. To do so, we introduce the Fischer model with bottlenecks. In the model parameterized by n, the population size is equal to n most of the time. So here, here, and here. The duration of those times is parameterized by a random variable s. But sometimes there is a catastrophe and the population size is reduced to this quantity here, nb. Here is 2 and here is 4, for time parameterized by a random variable L. We say that the bottlenecks are short if they last for one generation and long otherwise. We say that the bottlenecks are drastic if they are so strong that even in the limit when n tends to infinity, the population size inside the bottleneck is not infinite. And we say that they are soft if when we make n tend to infinity, the population size inside the bottlenecks also tends to infinity even if it is smaller. We say that the bottlenecks are rare if they happen in a time scale of order n and frequent if they happen in a smaller time scale. This is important because this time scale is the one that we use to obtain the Fischer diffusion from the Fischer model. In this work, we will focus on two cases. The short drastic bottlenecks, where the genealogy will be described by the symmetric coefficient. This is the first part of the talk. And the subordinated Kingman coefficient, which is the limiting object that we will obtain in the case of long soft bottlenecks in the second part of the talk. In the case of short drastic bottlenecks, the population size is described like this. So most of the time it is equal to n, and sometimes when these Bernoulli random variables that have a small parameter are equal to 1, it is chosen at random with some law that is characterized by f, where f is a measure in the natural numbers that will be important later. What happens to the frequency processes in this case is that as n goes to infinity, outside the bottlenecks, the frequency will converge to the Fischer diffusion. But when it encounters the bottleneck, the population size becomes so small that its evolution is very random. There is a lot of noise, so the diffusion can jump and do like this. And here again, it can jump. Formally, we have this result that says that the frequency process converges to the solution of this SDE, where we have a term corresponding to the Fischer diffusion, only if we are in the appropriate time scale, and the jump term that I won't describe any further because I want to describe the genealogy. The genealogies are given by the symmetric coefficient. The symmetric coefficient is a Xi coefficient or coefficient with simultaneous and multiple mergers. Multiple mergers means that I can have more than two blocks coalescing into a single one, and simultaneous means that I can have several mergers in the same event. Xi coalescents are extremely related to distributions Xi on this simplex delta. So delta is the set of interval partitions of 0, 1, where the sizes of the segments are given by these numbers. In the particular case of the symmetric coalescent, S is a measure on delta such that we have this. This f is the same f that we use to choose the population size at a bottleneck in our Wright-Fischer model, and these psi k are partitions of 0, 1 into k subintervals of the same size. So this would be psi 4. How the coalescent is obtained from these partitions of the interval 0, 1 is by doing the following. Imagine that we are here and we have an event at this time here. So before that, we had 6 lineages. We choose the partition psi 4. We will take this partition of 0, 1. We will throw 6 uniform random variables on 0, 1. So these two were in the green block. So they are painted in green and they merge together. So they correspond to these 2 blocks here coalescing. These 3 fall here, so they correspond to this block. And this one fell alone, and it's this one. And like this, we can construct the coalescent. So the theorem we have is that this symmetric coalescent, its block counting process is moment dual to the diffusion with jumps that I presented a couple of slides ago. Why do we say that this coalescent is symmetric? It is because it has this property here. What it means is that in the symmetric coalescent, these 3 trees have the same probability. These three trees have an event here where 6 blocks merged into 3 blocks, but the sizes of the blocks are different. In other words, in this tree, I can take the purple branch here and paste it here and obtain this tree. And in this tree, I can take the blue branch here, cut it and paste it here and obtain this tree. And these 3 trees in the symmetric coalescent have the same probability. We have studied the symmetric coalescent. We know its transition rates, which are here. We know that it comes down from infinity if we have this property here. And in the particular case of the beta symmetric coalescent, which is characterized by this measure f, we know its total coalescent rate lambda n, which is given by this. So it is of this order. And we know how it comes down from infinity. Normally, one can characterize the speed of coming down from infinity. Here, we have that it comes down from infinity like the exponential of a subordinator. What does it mean? We take kt to be the total number of blocks. We rescale it by the initial number of blocks so that k0 is 1. We also rescale time, and we have the convergence to this random variable, which is the exponential of a time change subordinator. The subordinator has this jump measure, and the time change is this one. We have characterized the side frequency spectrum of the symmetric coalescence using phase-type distributions. So this is a very efficient computational method to obtain the exact values of the side frequency spectrum. It is not an approximation, just a computational method. Arno and his collaborators developed it for lambda coalescent, and we extended it to the case of the symmetric coalescent. We observed that the symmetric coalescent has a peak in the middle of the SFS, like here. And we could compare it and find that for some species, we observe the same type of peak in the middle of the side frequency spectrum, which can mean that the population has undergone a demographic bottleneck. Now I will start the second part of the talk about Wright-Fischer models with long soft bottlenecks. I will focus on the particular case where Li, the duration of the bottlenecks, divided by n times bi, the population size during the bottlenecks, converges to a certain random variable that has a limiting distribution when n tends to infinity L gamma. And the time between 2 bottlenecks has, in the limit, an exponential distribution. What was conjectured already by Blas and collaborators is that in this case, if this is the sequence of population sizes, it is n, and then it decreases because there is a bottleneck. The bottleneck is characterized by L gamma, as we said, which is the ratio between duration and intensity. We can associate it to a subordinator that has jump measure L gamma, and that jumps like this. So this time here is this time here where the bottleneck started. What happens to the genealogy? You take a Kingman coalescent, you consider everything that happens during the bottleneck, and you glue it together because you accelerate time during the bottleneck. And you obtain this tree here that is a psi coalescent because you have created multiple mergers by gluing the events together. And it has this measure psi that I will describe later. To study the frequency process and how it converges to a diffusion, we may have some issues. Because the bottlenecks are long in this case, the process is not necessarily Markovian anymore. In addition, because during the bottlenecks the population size is small, we can have important fluctuations. So the frequency process may look like this. It can be very similar to Wright-Fischer diffusion outside the bottlenecks but then fluctuates strongly during the bottlenecks, and we obtain something like this. To overcome this problem, what we did is to introduce a new topology, d lambda. So d lambda is very similar to the Scholar-Hot topology. These terms here are exactly the same if you ignore the indicator function. This term is technical, and here you have the Lebesgue measure of the pink intervals that correspond to the bottlenecks. So you will only take the Scholar-Hot topology here because of this indicator in the blue intervals that do not correspond to the bottlenecks. So you will have convergence to a diffusion that has jumps. So you will ignore these parts, glue the other fragments together, and have convergence to a diffusion with jumps. This is what we have in the theorem. Here you have the jump term. The jump term depends on some psi, which is the measure of the subordinated Kingman coalescent, and this diffusion and the subordinated Kingman coalescent are moment dual. Here you have the characteristic measure of the Kingman coalescent. Here you have the L gamma, that was the intensity of the bottleneck, so the duration divided by intensity, and here the block counting process of the Kingman coalescent. To conclude, we have characterized the genealogies of Fischer models with bottlenecks under different scalings. If you have some questions, see you at the live discussion on Tuesday, August 25th. If you want to read our preprint on archive, it is linked here. And if you wish to contact me, this is my email address. Starting from September, I will be based in Barcelona, trying to apply population genetics models like those ones to cancer data.